And okay, yeah, this works there.
Oh, sim. Tem algum outro pendrive? Esse pendrive eu esqueci que ele é do Linux. Ele está formatado para Linux. Porque eu precisava que tivesse mix módicos para algumas coisas, que aí eu formatei para Linux. Ou eu posso mandar de algum jeito pela rede, não sei.
Foi mais rápido. Talvez seja o pendrive.
Acho que é uma pendrive. Apesar que tem aqui umas. Quantos desses?
Was a video pushing. Yeah, I want
Primeiro. Já conseguimos, não tinham perdido.
Isso aqui vai usar, né?
Pode ver. Isso funciona direto. Funciona, né? Com fissagem.
Funciona. Só eu tenho que clicar aqui dentro.
Vamos esperar, tá em só lugar, eu acho. Não.
A pessoa está aí, né?
Porta.
Ótimo. Não, sobre o andamento das coisas. Acho que está demorando.
Hello.
Aqui não tem nada.
Então, eu queria um pouco conversar contigo, que tu fez o Bicopê, e tocar essa outra parte que tu está ali e que a coisa está interessante. Há uma possibilidade, né, que tu estava ali pegando aquela aplicação do projeto do aquele que pegou com tocar isso, porque eu acho que tem uma boa conhecimento de tudo, e eu acho que tu dava para dar uma acelerada nisso aí, e aí, a partir disso aí, se a coisa funcionar, a gente pode...
Hello, can you hear me?
E a versão silenciada, tu estava em cima do data cobrar por isso.
Rafael, are you ready to start?
Hello.
Hello.
Hello, it's Rafael.
Hello, Rafael.
Desculpa, pouco só para conseguir ver.
All right.
Hello.
Hello. All right.
Can you hear me?
I'll just give you a quick introduction. So our next speaker is presenting remotely from the University of Federal Rio Grande do Sul in Brazil, and is going to be discussing SimGrid, which might give us the useful answer to the question of, will AMPI be effective on my application? And so we'll hear his presentation on that. Please start when you're ready, Rafael.
Okay, can you hear me well there?
Yeah, they can hear you.
Okay. So this work I'm presenting is part of my PhD here at the Federal University of Rio Grande do Sul. And I also work on it on a sandwich doctorate scholarship at Grenoble, working with Professor Arnaud, that's one of the leaders of the SimGrid project. And also had some cooperation with Lucas Schnorr, and of course with my advisor here, Professor Calhoun. Doesn't seem to be working. Okay. So that's the outline of my presentation. First, I'll give you some context, talk about SimGrid. Then I'll present our simulation methodology. Then some results on the validation of our methodology and some investigation of some AMPI parameters. And then the conclusion. So giving you some context. Parallel HPC applications are often written on AMPI, message passing interface, which is based on a regular single program multiple data programming model. Many of these applications are interactive, and this paradigm is very good for balanced applications. But if you have unbalanced applications, what you do? Some of them may resort to static load balancing techniques at the application level. Some of them not, because they may have some imbalance that comes from the input data or from the phenomena they are simulating. And this phenomena can evolve over space and time. For instance, our case study for this work is on CD, which is a seismic wave propagation simulator, and in it we have a wave that is propagating in space in time. So the load balance of the application changes depending on which step of this propagation we are. And handling this dynamic imbalance at the application level can be a nightmare. And then, what's the possible approach to solve this problem? Is over decomposition and dynamic process level load balancing as proposed by AMPI Chain++. And the way AMPI Chain++ does it is at runtime, which is, we think, the best way to do it. Our case study is on CD, which is a seismic wave propagation simulator developed by VRGM in France. It's used to predict the effects of future earthquakes, and it has many sources of load imbalancing. First, it has absorbing boundary conditions that makes the tasks that are at the borders of the region we are simulating having more computation than the ones that are at the center of the region. And also there are variations on the constitutional law of different geological layers, which also affects the load balancing. And there's the propagation of the shockwave in space and time. That is, there is a lot of energy that's being moved from the epicenter of the earthquake towards the edges of the region we are simulating. People at BRGM are trying to measure partitioning techniques and some quasi-static load balancing algorithms, but they have been proven ineffective. But the AMPI can be quite effective, as I have shown in a previous work. We were able, on a 192 core cluster at BRGM, we were able to achieve performance that is 36.58% better than the execution without load balancing. So when we are trying to take our application and get the best performance we can get by using load balancing, by using, for instance, AMPI, we have several challenges. We have to choose the best load balancing parameters. So, which load balancer is more suited for our configuration? How many iterations should be grouped together? That is, which is the frequency in which we call the load balancer? How many virtual processors will we use? What is the over decomposition level of the application? And also, preparing for AMPIs of free, there's some work to write data serialization code that may need some deep knowledge of the data structures in the application. And maybe you have to work with some, to remove some global variables or static variables. And engaging in such approach would deter some developers to try AMPI. So our idea was to find a way to predict what will be the benefit of using over decomposition with an AMPI load balancing without actually having to port our application to AMPI. So for this, we proposed a sound methodology for investigation the performance improvement of fire applications using over decomposition. Can you hear me? Hello? So what is SimGrid? SimGrid is a distributed systems and application simulator. It's a 15-year-old collaboration between France, US, UK, Austria, and others. It has well evaluated and validated full-level models for the network that account for topology and contention. And more importantly to us, it has SMPI, that's simulated MPI, which supports two ways of simulating MPI applications. The first one is trace replay, which is an offline technique in which we first run the application with the traditional AMPI and get some traces from this execution, some time-dependent traces, and then SMPI is capable of replaying these traces as many times as you want. And then there's online simulation, which is capable of running an unmodified AMPI application inside SimGrid in a controlled environment and using only one node running this application sequentially. And another characteristic of SMPI is that it embeds more than 100 collective communication algorithms from several different MPI implementations. Each MPI implementation implements several different algorithms for the collective communications. And then, what is our methodology for our simulation? Our approach is to implement the load balancing algorithms in SMPI, then capture a time-independent trace using one of two alternatives. Either standard tracing, that is running the actual application, which is fast because it's parallel, but requires more resources. What's the problem with the resources here? We need to have one core for each virtual processor, not for each processor. One for each virtual processor. Otherwise, we won't get accurate timings. And the second alternative is running emulation. By combining our application with the command SMPI-CC and then running it using SMPI run. The advantage is it requires only a single host. The problem is it's slow because it is sequential. Another thing we do is that a fake call to MPI migrate in your code. This call will generate an event in the trace that will be used in the delivery page to know when to call the load balancer. We also track how much memory is used by each PP and use it as an upper bound for migration costs. And this emulation may take some time, but it requires minimal modification or knowledge of the application. And the third step is to replay those traces we got in the second step as many times as we wish, playing with different parameters, changing the load balancer, changing the load balancing frequency, changing the network topology, and so on. So now we have a few key questions to our approach. How do we know whether our simulations are faithful? And how do we understand where the mismatch from our simulation to the real execution is coming from? It could come from the shadowing of the virtual processors, from our implementation of the load balancer that maybe not be exactly the same as the one that's in charge. Maybe a problem in trace capture. Maybe when we run the real application, we had some network interference from other applications. So at first, we tried to evaluate our approach with traditional visualization techniques like Gantt charts. But as you can see, it's very hard to compare executions with this. Even if we zoom in, it gets a little better, but it's still hard to compare. And now when I present these experimental results, I'll show you how we are doing this comparison. In these experiments, we tested two earthquake scenarios. The Niigata-Kent-Shuetsuoki earthquake, for which we run 500 time steps with a matrix of 300 by 300 by 150. And the Ligurian simulation, for which we run 300 time steps with dimensions 500 by 350 by 130. And we tested three load balancing heuristics: no load balancing, grid LB, and refine LB. Grid LB and refine LB are basically almost copies from chart++. The work method that is inside the load balancing chart++ is unmodified. I just removed the code that we didn't need for simulation and wrote some code to make our simulator provide the load balancing data to the load balancers and then gets the decisions they make from the load balancers. And for the hardware, we used a cluster from Grid 5000 that has in each node 2 AMPI of their own with 24 cores, 1.7 gigahertz, and infinite band network, plus my own laptop for the grid data. So here is the first visualization approach. What we decided to use for our comparison is the variation of the load distribution in time. So the evolution of the load distribution in time. Here we have a heat map style visualization in which in the vertical axis we have the resources, and in the horizontal axis we have the iterations of the application, and each small square in this visualization represents one iteration. The load of that resource between the previous iteration, the previous call to the load balancer, and the current call. But the problem with this visualization is that it's not so easy to compare one execution with the other. And if we had more execution than this, then we would have a huge visualization. Here we can have together that maybe grid LB is better than refine LB, and without load balancer there's a lot of imbalancing. But to make it easier to compare different executions, what we decided was to aggregate the data in space. That is, we will have only one data point for each load balancer call. And that's the result. Here we have the space aggregated run. In the vertical axis, we have the average load of each of those columns. On the previous visualization, we calculated the mean, so we have the average load And another difference is that now on the horizontal axis we have time instead of iterations. So we can see, we can also analyze the big span of the execution or of the simulation by using those graphics. So from these graphics you can see that for this scenario the simulated load behaves very similar to real life, and that in both simulation and real life, VLB is the best load balancing. But there is still some mismatch in terms of the total make span, and this is something we are still investigating. Here is the detailed view for the Ligurian simulation. You can see that it's not so easy as previously to tell which of the two is the best load balancer for this scenario. And on the aggregated view, we can see that once again the loads from simulation and real life are very similar, and that in both simulation and the real life, refinal B is the best choice. But once again, we have the mismatch between simulation and real life. And we can see also, for instance, the difference between refined LB and real LB is much larger in the simulation than it is in the real execution. I forgot to tell before, but the red in this graphic is the real execution, the AMPI execution, and the blue is the simulated execution. Now, we go to a second part of our evaluation. After validating our simulation, we began to explore some load balancing parameters. The first was the impact of the frequency of the load balancer. So, for this we call the AMPI migrate on every iteration, and then when we simulate, we change the frequency. That is, we remove some calls from the traces. So now we can change the frequency. Here we have the frequencies every 10, 20, 30, or 40 iterations. And on the vertical axis is the make spans of the executions. Red is no load balancing, green is grid LB, blue is refine LB. The conclusion would be use refine LB every 10 or 20 iterations. To get this graphic, we spend about 50 hours to get the traces, and about 6 hours and 40 seconds on my laptop to run the replay for the 3 different heuristics and the 4 different frequencies. The second thing, for that one we don't have real-life results yet. The second thing we analyzed was the impact of the over-decomposition level. Is the same here in the horizontal axis is we counted, and once again here is the time. The conclusion is using either grid LB or refine LB with 64. No, grid LB with 32 VPs or refine LB with 64 virtual processors. To get the traces from SMPI for this, it took about 5 days. And that's the main problem right now, the thing we need to solve in the next step of our work. That is, to change the decomposition level, we need at least 1 trace for each decomposition level, because the traces need to have the same number of tasks as the simulation. And the replay time was only 4.1 hours for the 3 different heuristics. So right now, our big problem is to reduce the trace capture time. And on real experiments, we get the same conclusion as in the simulation, only on 29 hours instead of 5 days. But for this we used more resources. We used a 16-node cluster, because this is running in parallel. Our previous was everything ran sequentially. So concluded the presentation. This is still ongoing work. Any comments are welcome. We presented our methodology for simulation of over-deposition based dynamic load balancing, like it's implemented in Charm++. We had good results in terms of load distribution, but some inaccuracy in terms of total mix plan. Our visualization of the evolution of the resource usage was quite useful to compare simulation with real life or to compare different load balancing heuristics. But we need to devise some way to speed up trace collection in order to facilitate the analysis of different over-decomposition levels. And one thing we were wondering is if there's some way to get similar traces from our input traces straight from Charm++ or AMPI. One idea we had was if we could get those traces from an AMPI execution, we wouldn't need to have as many processes as we have. We needed to do the tracing with SMPI or with a real execution with AMPI. That was it. Here I have some acknowledgements. I thank CNPq for my PhD scholarship, Jacobi that financed my Swedish doctorate scholarship in Grenoble, and the HPC for Energy project that this work is also in the context of this HPC for a project that's an European H2020 programming project. That's it. Thank you. Questions?
Let's thank our speaker. We see the mics around, so people should, if you just get any round of questions.
Well, I feel like you might be able to answer some of his, his questions from the immediate previous slide.
Yeah. Have you tried using the load balance simulator infrastructure inside of Charm++ itself?
Sorry, the sound is a little. I couldn't understand you.
Yeah, we might just have to pass that around.
Maybe you can. I'll try to. Yeah, I raised the volume here. I see.
Have you tried using the load balance simulator inside of Charm++ itself? You can do a run and actually have it record the balance and then record and what it would project to do with such an imbalance.
I don't know if I understood yet. All right. What we wanted we were wondering if we could do is to get the traces that we use as input to our simulator from inside Charm itself. I don't know. I'm sorry. I don't know if I understood your question. Maybe you can write it there.
I believe it is actually possible to produce those traces directly using the built-in tracing framework. We'd have to build a different capture mechanism for output, but the hooks to do so are part of the tracing infrastructure. We should talk about that offline.
The traces that would be used, for instance, to run Big Sim.
Yeah, it'd be a different format, but the hooks to gather the information is already in the system.
Yeah, we were wondering if you could get from your traces, get the traces we want, maybe convert it some way or something like that.
I think it's a possibility. We should look into that.
Yeah, that's one thing we had already talked about it. It was one of the last things I discussed it with my French advisor. Because it would be a way to get the traces much faster without needing as much resources as we would need with AMPI. Because when with traditional AMPI, the problem is we need too many processes and they can't share the same core. Otherwise, we get inaccurate times. But as charmer already schedules those virtual processes sequentially, then we wouldn't get the inaccuracy we would have if we tried to do this with AMPI.
Right.
So,
Yeah, we should definitely follow up on that.
yeah, maybe, yeah, that was one idea. Maybe we can keep in contact to talk about that.
Any other questions? All right, well, thank you, Rafael.
Thank you.
Uh,
Bye. Bye.
goodbye.
A questão da
Boa.
Not sure if that's the right answer. Michael, should we just log out of this session, or? Next presenter is PhD candidate John Calhoun from here at the university, who will be introducing important ways to speed up your application output using compression.
All right, I will. All right. Okay. All right. So, as Eric mentioned, my name is John Calhoun. I'm a PhD student here at the university. I am advised by Professors Luke Olson and Mark Sneer. And on this project where I'm looking at using lossy compression to improve checkpoint performance, I've been working with Frank Capello and Sheng Di from Argonne National Labs. So the current state of HPC and going forwards is we have this data movement problem. Computation is so cheap, data movement is so expensive, and something I really wasn't aware until I started doing this research, it's even more expensive power-wise. So here is a talk from a micro keynote from 2011, and it shows that the power required to do a 64-bit double precision FMA is measured on the order of picojoules. Doing a DRAM access is orders of magnitude more expensive power-wise. So going forward, it's really we have free computation with respect to moving data around. So what are we going to do with this free computation? And what I'm going to look at is let's try to compress the data. It's going to take a lot of energy to move data around in future systems. If we can move less data around, we're going to save energy. But the way that I'm going to do it by adding error. So the first thing I have to do is I have to evaluate, are simulations able to handle error added in? All right, so in my work, I'm going to be using Charm++, and Charm++ has native support for checkpoint restart. We have the ability to checkpoint to partner nodes, this double in-memory checkpoint. We also have the ability to checkpoint to permanent storage. And no matter how many times you checkpoint to partner nodes, eventually you're going to have to put a checkpoint in the permanent storage for reasons of I would like to run longer than my time allocation. So this is really the low-hanging fruit. And what we're going to look at in this presentation is, can we improve the I/O performance of an AMPI application by using lossy compression? So why use lossy compression? Why not use lossless compression? I mean, if I decompress from a lossless scheme, I'm going to get the exact answer. I'm going to have the same simulation. And the problem with that is lossless compression for floating point data is very, very hard. Very, very hard to actually get any compression. So here are some state-of-the-art lossless floating point compressors specifically designed to compress floating point data, and the compression factor that they're able to achieve is a little bit over 1. The max there, I believe, is 2.13. And this is over real HPC data sets. Essentially, I could go from 64-bit precision to 32-bit precision and get, for the most part, exactly what they have there. But let's look at using lossy compression. So the standard lossless schemes, they don't provide good compression for floating point, but lossy compression, they allow us to compress a lot more. By how much more? I apologize if the text in this figure is small, but this is taken from an IP DPS paper from this year that shows compression ratios for some state-of-the-art lossless compressors, and you're talking about compression ratios of 1,000, 50, 60, 70, vastly higher than what you can get with lossless compression. The error tolerances for this figure were set at 1e minus 6, but how do you set an error tolerance? How much error can the application handle? And that's what we're really going to be looking at in this presentation. If we restart an application from a lossy compressed checkpoint, is it valid? Are we going to have a simulation that means something to us, or is it just going to be wasting CPU hours, wasting dollars? So my argument to you is, well, the first is we've already embraced various amounts of error by running scientific applications. We are using floating point arithmetic. Floating point is approximating this continuous spectrum. We have accepted this and we use it every single day. We've also been using numerical methods that are only accurate to a certain degree. We have, let's say, first order accurate methods, second order accurate methods. We know that we cannot resolve error in the problem more than what the numerical method says we can. So let's leverage these ideas and sort of think about the error from a lossy checkpoint in the context of the mathematics of this application. So all of these lossy compressors, they allow you to specify how you want this error in the simulation. They could say, we will preserve X number of bits in the floating point representation. We will bound the relative or absolute error at every data point. We will bound the relative and absolute error of the entire vector or the entire domain that you provide us to compress. But how should we evaluate this error? Is it good error? Is it bad error? I mean, I could say I can get a very, very good compression ratio by throwing your data out the window and reloading from whatever malloc gives me. Chances are it's not going to be a very good simulation, but you save a lot of money on and a lot of energy on data movement. So what we're going to look at in this talk is the accuracy of numerical methods. So we know that when we're running some schemes, they are accurate, big O, H to the P, they're P-order accurate. And based upon the discretization of the problem, we can calculate sort of the accuracy in floating point values with the idea of, should we go and restart from a lossy compressed checkpoint that has added an error less than your truncation error, less than your accuracy of your methods, it should be invisible to the mathematics, therefore invisible to the simulation itself. The error that we are going to be adding in is hidden due to the mathematical accuracy of your simulation. So to understand this, we will first look at two simple PDEs, a 1D heat and a 1D advection equation, to sort of understand this idea. The compressor that I will be using is the SC compressor version 0.5.5 that's being developed at Argonne National Labs. All of my data for this presentation is 64-bit floating point, and we're checkpointing just the PDE state, which would be the state variables from the PDE simulation. So here we have the simulation for a 1D rod. We have the ends of the rod are fixed at a constant temperature, and there is a point source in the middle. So if you would go and evolve time, you get a nice sort of a hat-shaped sort of rooftop V constant solution, or time-independent solution. So here we have the length of the rod on the x-axis. On the y-axis, we have simulation time. which every dashed rectangle there is itself a time step. So at the beginning, we have no error because we haven't restarted from a lossy compressed checkpoint. At this time step here, we check a checkpoint and restart the simulation. And you can see that we've added various amounts of error to the simulation. And as we continue to evolve time, that error becomes removed, or is removed. And we can compress again, and well, the error is removed again. This is a nice property of the heat equation that we're approaching this sort of steady-state solution. It's removing errors for us. And we already know that there are some applications that can tolerate errors, such as iterative linear solvers. But how does this error that I've shown here relate to the discretization error of the problem? So the solid black line is our discretization error, is the accuracy of the numerical method, or the discretization of the problem and the numerical method that I'm using. And the error that's from the solution to the lossy solution is shown in blue. And even when I do a checkpoint, I've specified the tolerance to be less than discretization error. And so all of this error that we've actually added in is hidden due to the mathematics. Looking at the result, it's qualitatively the same as the original result. And even when you do multiple checkpoints, you aren't adding an error that's over your discretization error. So you're not changing the simulation according to the mathematics. Let's contrast this with an advection equation. This advection equation is simply, you have a sine wave that is propagating to the right. So it's just sine x going to the right, and everything that pops off one end of the screen, we're going to put it back on the other. So we have periodic boundary conditions. Sort of the same setup as before. We have our domain on the x-axis and the y-axis, the simulation time. Here there are multiple time steps between any color change. Here at this time, we restart from the lossy compressed checkpoint. And you'll notice that we instantly have error through the domain. We don't restart from another lossy checkpoint until this point here, but what we can see is the error itself is being shifted through the domain. The color itself is relatively constant. So this is the property of the advection equation, is whatever you give it, it's just going to propagate it whatever direction the flow is. And every time you restart from a lossy compressed checkpoint, we're accumulating error. So not only, do you have a question? Yes. Mm-hmm. Currently, we haven't looked at algorithms such as that. That's one of the things I'm going to be looking at this summer. Yeah. Yeah. Right now, we're just saying mathematics can tell us some stuff. Let's take the low-order mathematical approach. Yes. 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 This is sort of the, I guess, yeah, the first order. Yeah. Yes. Yes. Where was I? The y-axis is the simulation time. So I plotted the error in the solution. Oh, the color is the error in the solution. So white is there's no error. Blue, you're off by a negative amount. Red, you're off by a positive amount. Yes, yes, yes. Yeah, this is the absolute error. And so you can see that this PD, it's propagating. So we can't just say compress the discretization error and be fine. Well, that can be true, but PD properties will either remove error or keep error and propagate it in. So you would need to think of what is my PD actually doing? What are the terms in the PD working on? And if we look at the error added in relative to discretization error, we can see this as every time we do a checkpoint, we're just adding in error. We sort of get some removal of error, but it's sort of approaches an asymptote where the error stays in the simulation. So if we kept restarting from this lossy compressed checkpoint, eventually we're going to add in error and we're going to diverge our simulation. So let's look at this in the real application. So the application that we've selected is the XPAC Center's PlasCom-CM code. It's a multi-physics plasma code developed here at the university. For this, our checkpoint restart is going to be accomplished by running it through AMPI. We've modified the pack-unpack framework to, before we go and save the state variables of the simulation, we are going to run a lossy compressor over them. The problem that we're solving is a Navier-Stokes flow past cylinder. We have our various problem discretization. So what types of compression factors are we able to achieve on this code? So based upon the error tolerance, we can have anywhere from roughly 80 to 90x compression ratios, all the way down to about 2 or 3x, depending on how much error you want to add into the simulation. Okay. All right. So based upon whatever accuracy that you're solving to, you have a wide selection of error choices to make. But perhaps compressing to a very, very tight tolerance has a high overhead. So if we look at the time to compress, which is the solid lines, and time to decompress, we see that throughout the error tolerances present here, throughout all of our state variables, density, energy, the x and y momenta, it's, for the most part, roughly the same. There are some variations, but for at least this data set, it doesn't seem that to get a very, very tight tolerance, to get a very, very small error in my solution, it's going to take a long time to compress. So what does this do to the simulation itself? Here we're using a higher order integrator, and the system itself is accurate to 1 times 10 to the minus 14th, if you work out the mathematics that way. So we decide that we're going to compress, or excuse me, 1 times 10 to the minus 13th, so we're going to compress to this 1 times 10 to the minus 14th. And so the simulation is shown here. This is the momentum, and this figure here will be the error in the solution. And so initially there's no error until we restart from a checkpoint. And we can see that the error appears throughout the domain. Every 250 time units, we restart from another lossy checkpoint. And what we can see there at the end is there is some accumulation of this error. So error is being removed, the flow is moving out of the domain, we have non-periodic boundary conditions, that's nice, but if you look at the areas where there is virtually no momentum, the error is accumulating. So this is saying that, well, we need to think more about the application itself. What is the application doing in order to further design lossy compressors? We can't sort of blindly go about just compressing below discretization error and expect to get good things over the long term. This next video, I would like to pose a question to you all. We have the correct simulation on the left, and on the right, we have the lossy simulation. And I would like for you to try to guess, what is my error tolerance there? Would anyone like to guess? Let's play it again. Ten to the negative 2. You were actually absolutely correct. It is 10 to the minus 2. So, excuse me. Visually, there's really no change in the simulation. Perhaps when you dive deeper to analyze sort of on a more mathematical statistical basis, there's going to be some difference in the solution. But what this is saying is we can also use checkpoint, lossy checkpoint to get cheaper visualizations. For the compression ratio for this was about 40 or 50x. So if I'm doing lots of these visualization files, I'm just looking at the simulation, what happens sort of at this high enough level, I can produce these simulations very, very fast. So what have we learned, and what do we need to do? So we found out that you can restart a simulation from a lossy compression checkpoint. You can keep the error that you add in below the error of the mathematics. So at least at that level, we've said that the simulation itself can be accurate. But we need to do more analysis, and I'm sort of at the limit of what I know about these applications. Like the comment earlier, there's stuff that we need to preserve. The application scientist knows what we need to preserve. We should talk to them and show these results to the users of the XPAC code and let them help further guide us in what we need to do or guide us when we're furthering design this compressor. So we've looked at this in the context of one full-scale application. But we need to look at in the others, and chances are we'll find that what works well for one application is not going to work well for another. But what I would like to say, go back to those two PDE model problems, is say different parts of PDEs either attenuate or propagate or maybe even add in error. If we can sort of find out what components of the PDEs that we're solving, what is their associated, how they handle this error, we might be able to find a order of better accuracy about what we should compress to, not just looking at just discretization error. But this is a relatively new project, so if you have any questions or suggestions about what you think would be interesting to look at in the context of lossy compression, I would be interested in hearing. Yes. 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 Yeah, and like turbulent flow or something. Yeah, yeah. Yeah, and that's one of the applications I'm looking at now is the NEC5K code. It's an incompressible, very turbulent code, and I haven't got any of the results from that, but we are expecting to see very, very low compression ratio, compression factors, and still it might be even more difficult to determine if the simulation is valid or not. But Phil? Yes. Yeah, so I would say that there are compression schemes that work sort of both ways. So some compression schemes, I give it a data vector. Part of it will have a high degree of error, and part will have very, very low error compared to the error bound that you set. Others will try to get right up to your tolerance for every single point of that vector. And so that's sort of a nice uniform error that may be easier to analyze in the context of conservation. And then you could also think that not every variable in the simulation can be compressed to such a high error if it's going to directly affect some conserved variable. Mm-hmm. Yes. Mhm. Yeah. No. It's like the compressor that I use here. It's sort of a linear predictor. As long as you're in the bounded error range, that's what you get. Perhaps in a future revision, we will go and look at exactly that, and that's another thing that I'm going to be looking at over the summer. Yes. Different compressors do different things. Generally every compressor takes the dimension of the array into account. So you can look at spatial neighbors. Generally all of them particularly just look at spatial relations. They either look sort of the memory layout as I'm walking through the array, or they look sort of on like an image of the application to sort of say this section of the domain, let's compress on that. One thing I haven't seen is this done temporally, is looking at deltas from your previous checkpoint that you stored.
Thank you, John.
Thanks. All right, sorry about that.
Our next speaker, Dr. Edgar Solomonic, is returning to us from ETH, and he'll be telling us about his Cyclops multidimensional tensor framework, which is based on some ideas of his own and a little bit of inspiration from Charm++.
Thanks, sir.
Really finicky. Make them stop.
Take this one all the way and leave that one. Okay, yeah, we're good.
Bounce off the bottom.
Okay. Well, it's great to be back. I think I was last at a Charm++ workshop presenting 6 years ago, and I look forward to being at University of Illinois in the fall. I wanted to start by a little bit of motivation of kind of where Cyclops tensor framework lays with respect to existing parallel languages for multidimensional arrays, as well as kind of more general frameworks that support distributed arrays. And on the other side, numerical libraries that support parallel computations. So for example, there is hierarchically tiled arrays, and Charm++ has multi-phase straight arrays, and the Charm++ multidimensional char arrays themselves allow one to write multidimensional array codes and facilitate that. There's also global arrays, UPC, Titanium, and high-performance Fortran, which I think all have various level of support for multidimensional array computations. On the other side, there is the numerical methods frameworks, which in particular work for matrices and vectors. And they provide various types of methods that you can use to various degrees. Scale-up-back provides density algebra routines, as does Elemental and G-Plasma. Petsy and Trulinos, I think, primarily focus on sparse iterative methods, but also have primal support for matrices. So these are kind of two very different ends of trying to approach some of the same problems. I think many applications have experimented with using both types of frameworks to implement certain iterative solvers and applications. The more general frameworks that we have on the left typically allow the user to define an arbitrary distribution and allow for transformations and scheduling, but they only have usually somewhat limited support with respect to the scope of operations. While the numerical methods libraries provide very powerful methods, but have performance that depends on the implementation of each particular method and don't allow many transformations of the data layouts. So in one case, we have some limited API for expressing array computations and data transformations, but not a lot of power in terms of the number of operations that we can execute without implementing our own functionality. And in another case, we have this broad set of functions for different solvers, for different dense matrix factorizations that are very powerful, but may not necessarily perform well and don't necessarily allow for general application development and are hard to tweak for any particular method. So once we then think of even higher dimensional arrays, so going from just matrices to tensors, support within, I think, many of the array languages becomes more rudimentary. You're more likely to encounter bugs, and there's less features that are primarily available. While for the matrix libraries that we have, usually there is essentially no support for higher order tensors. You have to do the work yourself if you want to work with a higher order data set, to fold it into a matrix representation and operate on it. And some methods like tensor factorizations, there's just no distributed memory libraries for. So kind of the goal of this talk, and I'll be introducing Cyclops Tensor Framework as an approach that tries to, in a way, get the best of both worlds. To have a limited API that at the same time allows for rapid and efficient implementation of various numerical methods with tensors, so with higher dimensional matrices and higher dimensional arrays. The particular primitive that CTF was from the start designed to leverage are tensor contractions. And so a contraction involves two tensors that, and here I use this array index notation, so these are not matrices, they're higher dimensional objects. So one might be of order s plus t, this is the result, and this is order s plus v contracted with order v plus t over v indices. But in general, these v indices that you contract over can appear in as any subset of these indices. And so this type of tensor contraction primitive generalizes a lot of the very, very basic matrix BLAS operations, basic linear algebra subroutines, including the vector inner product, matrix-matrix multiplication, matrix-vector multiplication, and the vector outer product, and going towards higher order objects, the tensor times matrix product, where you have one operand is some higher order tensor, and the other is a matrix, and you contract over one index. This particular primitive is the foundation of many tensor factorization algorithms, which decompose a tensor into a multilinear product of either lower order or lower rank tensors, and is quite popular in a variety of applications. So in particular, the alternating least squares algorithm is based on this TTM, tensor times matrix product. But there are many other applications for tensor computations for tensors of order higher than 2, including higher order numerical schemes. Also within computer vision and graphics, you typically have data sets that correspond to many images over time, or many images over time from many angles, which are naturally represented as tensors, and much of the analysis is simplified when working in that form. One particular application that is extremely popular right now are the convolutional networks in deep learning. There you often have, again, these kind of image and video data sets, which are correspond to order 3 tensors, and you do partial convolutions along essentially subsets of them to map to new 3-dimensional tensors or sets of 3-dimensional tensors. And these are actually often done with matrix multiplication, despite the fact that that's not really being the asymptotically optimal algorithm. So in fact, they are currently being done with tensor contractions. Okay. There's also a lot of applications for solvers for the mighty Schrodinger equation, which leverage tensors, because there you have an equation that really has this exponential scaling and it really requires consideration of higher order moments. Within the physics community, especially solid state physics, one of the most popular methods currently is the density matrix renormalization group, which expresses systems as essentially lattices, where at each lattice site you have a tensor, and overall you have a multilinear equation of tensors representing your system. One application that I will focus on was the application driver for the development of Cyclops tensor framework, in a similar way as MD and OpenAtom were some of the applications driving the development of Chum++, is the couple cluster set of applications. And one thing that really attracted me to this set of methods is the, I think, richness numerically that they have, and also, I think, the gap that one can still try to exploit with respect to making them faster. They typically have polynomial order scaling that is quite high and involve evaluating a large set of tensor contractions. So a little bit more about that. What electronic structure methods do is try to solve the many-body time-independent, which means just static, Schrodinger equation, which allows you to calculate the energy of an electronic system to high accuracy and subsequently to model things like chemical reactions and basic properties of materials. So the couple cluster methods are very kind of higher order accurate methods that try to get you really a lot of, let's say, digits with respect to your ground state energy and further calculations. And there are three common types. The most common is CCSD, CCSD-T, and CCSD-TQ. And these involve CCSD singles and doubles, T triples, Q quadruples. What this means is an excitation of either 1, 2, or 3, or 4 sets of electrons to new states. And essentially, each one of these methods, as you go to higher and higher order, considers the interaction of larger and larger sets of electrons taking over a larger and larger set of orbitals, which you can think of as basis functions. So for each one of these methods, you essentially have a tensor that corresponds to having modes for each set of electrons. So either 1 electron, 2 electrons, or 3 electrons. Those are 2, 3, 4 of the modes of this tensor T, plus as many modes for the basis functions. So the order 4 tensor that you're solving for in the CCSD method has 4 modes, 2 of them corresponding to electrons, and 2 of them corresponding to basis functions. So comparing this, for instance, to calculating all of the forces in molecular dynamics, there you have a tensor, a matrix, whose modes correspond to particles and particles. So you can essentially then derive equations that solve for this tensor T and obtain an energy that's consistent with respect to a derivation of the mean field Hamiltonian, which itself can be represented as a 1 electron and 2 electron interactions, a matrix and a 4th order tensor. And what you end up with when you essentially plug the ansatz motivated by the couple cluster into the Schrodinger equation is this huge set of terms which essentially correspond to all the possible transitions of electrons towards the higher order states. And some of the equations start to look like multilinear products of these tensors. So this is T times F contracted over 1 mode, and this is T times V times T contracted over 4 modes. These are then factorized into bilinear products of tensors, and you essentially get a lot of tensor contractions that can all be reduced to matrix multiplications, but require the reordering of the tensor modes in various ways for each multiplication. Within these equations, you also almost always have a lot of symmetry in the tensor representation. So the T tensor is antisymmetric with respect to interchange of these 2 modes or those 2 modes, which means that you can, antisymmetric means symmetric with an interchange of sign. So you can represent the data storage and also lower the contraction cost by factors proportional to the amount of symmetry in the tensors. So, and this grows essentially exponentially with the number of modes, number of dimensions. So for the T tensor, you can use a factor of 4 fewer elements if you exploit the symmetry. So typically, software libraries are written in order to leverage this. So in terms of the number of terms that appears in CCSD, you have 45 terms that look something like that, which are the kind of different transitions. And although only 5 to 10 of them will be leading order in cost, so you have to kind of focus on computing those most efficiently, but you also have to support a large variety. And as you go to the higher order methods, you get essentially an exponentially growing number of such terms, although again, only a small subset of them will be leading order in cost. So actually just a part of the CCSD equations actually factorized into bilinear products looks like this huge set. And what I'd just like to point out is essentially you're contracting these higher order tensors in all types of different ways. So you sum over some of the indices and others, and you get these order n to the 5th or n to the 6th cost contractions if each of the modes has length n. More generally, it's number of electrons and number of orbitals, which are somewhat different. And you have to be able to execute all of those efficiently and transition between the data layouts required to execute those. However, each one of them can be just done as a matrix-matrix multiplication after reordering. At least that's one approach to doing it. But you have to be able to do the reordering quickly, and this becomes a bottleneck, especially when you're in distributed memory and you have a data movement cost associated with the reordering. So CTF Cyclops tensor framework was motivated with respect to solving such equations and more generally just supporting tensor computations. It's a distributed memory library based on AMPI and also with threading provided by OpenMP and potential acceleration by CUDA. And it has a kind of simple interface that's based on Einstein summation, so avoiding the summation signs and just describing everything in indexed form, which is actually what is done in quantum chemistry. And it primarily targets tensor contractions and also tensor summations, as well as essentially arbitrary functions on tensors, as I'll show. You can also think of this as essentially functions on multidimensional arrays and ways to interact pairs of multidimensional arrays. It also was built to support symmetric packed storage, so only storing the unique part of each tensor, and it now also supports sparsity. For both of these, we achieve nice distributions via what's called a cyclic layout, which I will explain. But first, to show how the interface looks like and explain a little bit more what Einstein summation means, if we just want to do the Jacobi iterative method, which primarily consists of a multiplication of a matrix by a vector, we can do it as such. So this is the only line of C++ code that is actually CTF code, and I've just added these comments to try to explain what's going on. So the loops over I and j over these indices are implicitly inferred from this equation. The matrix vector multiplication is here. Then we have essentially a summation. We subtract from the right-hand side the output of this matrix vector multiplication, and we scale each element, so we compute pointwise product with D, all in this kind of simple notation. Then we can compute the residual simply like that. And this norm2 function is specialized to compute the norm of a vector or a matrix. So this is the Frobenius norm, actually, for any tensor. And so now to take out the commented out loops and also show the part that I skipped for Jacobi iteration, which involves subtracting out the diagonal part and the off-diagonal part. So R here will be the off-diagonal, and this means, if you can imagine 4i and then 4i, so this touches only the diagonal of R. We set that to 0, and we copy the diagonal of A into this vector D, and then define a special function that allows each element to be inverted just by, again, applying that to this tensor matrix. So this type of index notation is particularly powerful once we go on to expressing higher order contractions, in particular these couple cluster methods. So this is code that appears within the Aquarius framework, which was developed by Devin Matthews. We both started working on this domain while we were interns at Argonne now 6 or 7 years ago. So he's a quantum chemist at UT Austin, and he developed this framework on top of CTF, leveraging it to do each one of the tensor contractions, and really CTF dominates the cost of his work. But here you can see that equations that involve contraction of two fourth-order tensors that would have normally required one to write 6 of nested for loops and then manually do a parallelization over some subset of the indices are now just written as one line of code, and the framework takes care of doing all the work of parallelization and scheduling automatically. So since kind of our initial effort with the queries, CTF has also been adopted by some of the bigger players within the higher order electronic structure community, including QChem, VASP, and Sci4. And these are, for many of these, CTF now allows essentially distributed memory capabilities with very little effort with respect to what was already there. Okay, to talk a little bit more about how CTF works, it's a little bit more about the interface, is I kind of so far have just talked about contractions and haven't actually talked about how to initially fill up the tensor with data or extract the data. We do that essentially by this type of global array-like access where but also bulk synchronously. So each processor will write some subset and read some subset of the data defined just in key value form. And the actual layout of each tensor, so its decomposition, is hidden from the user, although one can define an initial distribution and insert the data that way somewhat faster. We also allow slicing, so extracting submatrices, or more generally subtensors, blocks of the tensor via, again, a simple routine. And we can also sum those and operate on them directly. And one can also extract different subtensors onto different subsets of processes and then break up the computation into pieces. You can also extract any permutation of the tensor. So you can imagine permuting the rows and columns of the matrix and then extracting a block of that. What we call the permute function allows this to be done essentially in one line of code. And again, each processor can, or set of processes can extract a subset, and one can then work on subsets of processes in different parts of the computation. Now, to talk a little bit about the cyclic layout and why we use it, as well as to highlight the kind of difficulties in storing a symmetric matrix. So here we have this funky representation of a symmetric matrix, and this is the part that we actually want to store. So only the lower triangular part, that's the unique part of the matrix. And if we just use a very naive block layout of what the matrix originally was, then we see that one processor owns nothing, some of them own a half of a block, and one owns a full block, so we have load imbalance and difficulties with that. If you go to a block cyclic layout, which is what's used within, for instance, Scale-up and many linear algebra libraries, this would mean that each processor owns a sub-block with some cyclicity factor, which here is a factor of 2 in each dimension. You still have some load imbalance that's now smaller, but processor 1 owns a lot more than processor 2. So we use a cyclic layout, which means that essentially each second processor will own every second element in each one of the dimensions. And this allows one to extract essentially a piece of the symmetric packed layout matrix that is as close as possible to the same size in each processor. And once we actually extract this piece, which is completely non-local in some sense, we again have something that looks like a local block. And in fact, the local blocks that we have on each processor look like the overall symmetric packed laid out distributed matrix. So if we had a kernel for sequentially working with such a packed layout, we can now hope to apply it to each sub-block here once we've used the cyclic layout. It's still not perfectly load balanced. So as you can see here, this processor is missing one diagonal with respect to the other processes. But this kind of diagonal is small enough, although it can be larger for higher order tensors, that we just use padding and via this ensure that every piece of the computation is of the same completely regular size. And in fact, by kind of taking this approach, we reduced a problem that used to be treated with dynamic load balancing, in fact. So NWChem, for instance, which is a kind of a different framework for computing coupled cluster methods, deals with symmetry by actually extracting blocks as we had in the block layout, and then doing dynamic load balancing in order to deal with blocks that don't exist, that are symmetric or smaller, that are essentially in this upper part. And by using a specialized layout, we've essentially made this problem completely regular. Okay, so one way where I think CTF really gets close to some of the ideas that have been employed in Charm++ is in its use of over-decomposition. That is assigning multiple blocks of the tensor to the same processor. And we do this for different reasons than Charm++. So in Charm++, this is done because the blocks essentially contain different size subsets of the computation frequently. And by over-decomposing, we can then hope to balance out the blocks, so each processor potentially owns a different amount, and the overall computation becomes load balanced. In CTF, we do it so as to decompose the tensor in any way that we want with respect to the overall virtual topology. And this allows us to essentially preserve symmetry in the layout for an arbitrary amount of given processes. So if we want to map to a 4x2 processor grid, and we're given an order 3 tensor that's symmetric in all of the modes, we would like to decompose it such that the dimensions of the decomposition match in each dimension. And this allows the cyclic layout to preserve this nice symmetry. And we can do so by breaking it up into 64 blocks and assigning all of these 8 blue blocks to this processor. And we do similar layouts for this matrix and this tensor, which are also very symmetric packed layouts. And so we kind of have leverage over decomposition to preserve the structure of the problem, and at the same time to work with an arbitrary number of processors. So we do want to have everything be general. Okay. So to talk a little bit more about the details of this decomposition and mapping. So I guess these 2 points I've already mentioned. But the way the mapping logic works is that we try to map to all possible processor grids. And the set of processor grids is based on some starting physical topology. So on a machine like the blue gene, either P or Q, we can actually infer the topology that we're given, and we work with that torus as the basic topology, the subset of the torus that we're given. On kind of a more general network, we have some subset of nodes, and we interpret that subset as also a torus network, except with the maximal number of dimensions. So essentially factorize number of processes we're given and say that this is a torus network. Then we form all of the topologies by considering all foldings of this base topology. So given a 3x3 an order 3 torus, we'll consider all foldings into order 2 tori, into order 1 tori, and so forth. And given a factorized number of processes, we'll consider all combinations of those factors, which all form essentially different ways to decompose and map each tensor to the processor grid. And for each contraction, we then tune overall mappings, so assignments of the tensor modes to these processor grid modes. So this allows us to essentially consider all possible layouts, for instance, for matrix-matrix multiplication, and more generally, all possible layouts for tensor contraction. Maybe all possible is a step a little bit too far, but a very large amount. And especially given a nice number of processes, so a factor of 2, maybe with a few factors of 3, we actually, I think, effectively consider all layouts that are worth considering. Then for each of these mappings and for each of these decompositions, before actually going to that decomposition, we ask, okay, how much will it cost to run the contraction given this decomposition? And since everything is regular, we can essentially derive the communication costs both in terms of the memory bandwidth, so the traffic between some cache and memory, as well as the data traffic moved between processes a priori before picking the right distribution. And based on that, we can pick the best one. And we also do this using all of our processes, evaluating a different subset of the mappings. So we leverage parallelism at runtime in order to pick the best decomposition. And so when we actually have sparsity, we also try to estimate the load imbalance caused by any given decomposition. And there's also, of course, the cost of going to and from decompositions. And for that, this is also something that's part of our performance model, but it's also something that we've put quite a lot of effort into optimizing. So I already mentioned that we had these kernels for writing and reading a subset of the data to the tensor. And these essentially correspond to a sparse redistribution. And to do that, we have an all-to-all-V as well as some binning and sorting. So this is fairly expensive sequentially and is a somewhat unstructured communication pattern. But it is extremely general in the distributions we can express. The redistribution type that we've optimized most and is also quite powerful and the one that's most used within actual execution of methods is redistribution from one mapping, so one physical topology and one assignment of tensor modes to those torus modes to a different one. And at first we would actually do this by explicitly iterating through all the elements and computing where each one needs to be sent. Recently, we actually were able to derive an analytic recurrence for any two mappings and any types of symmetric packed layout for how many elements will be sent between a pair of processes. And this thing actually is very complicated, but it is possible to do analytically, and this has saved us quite a bit of cost. Then we essentially pack subsets of the messages that correspond to the messages defined by the lowest, the dimension of the tensor that moves most slowly. Most quickly. And then try to also optimize that in more manual ways by nested loops that are template instantiated and threading. So this kernel is really complicated, and I'm skipping a lot of the details, but essentially we've put a ton of effort into making these dunce-to-dunce mappings be as fast as possible, to the point that now we're essentially always dominated by the communication and the local work of actually determining where each kind of subset of the data needs to go, which is in general a fairly irregular redistribution pattern, is now low order for the most part. There's also block-to-block redistribution, so if you want to go from the same virtual decomposition, so the same number of blocks of a tensor, to a different assignment of the blocks between processor grids, we can do that more cheaply. We do that by just sending the blocks in point-to-point messages, and we don't need to iterate over the entire data set and figure out where each given piece of data goes. Okay, now to highlight the benefit of doing these searches over the topology over partitions and actually exploiting physical topologies, let me just highlight a matrix multiplication result that we've achieved in the BlueGeneQ. So with respect to scale-opac, by leveraging what's called rectangular collectives on the BlueGene, which are the fast broadcasts you can use when you use a regular subset of the processes that nicely matches the torus. These collectives essentially benefit your performance by something like 100x. They're much, much more efficient than regular binomial collectives. And by leveraging those for a rectangular matrix multiplication, meaning that the matrices aren't square, yeah, so QBox has used this matrix multiplication, going to step ahead, to do orthogonalization within density functional. Yeah, I put the slide after we talked at lunch. I wasn't actually going to do this, but yeah, so we can get a very large speed up by being a little bit smarter about the topology. But this is like an extremely basic usage of the framework in some sense, right? So this is just matrix multiplication. So yeah, that's why they use it. Right, yep. Okay, but it's much more fun to implement a couple cluster methods because they're much richer in exploiting the full generality of what the framework can do. And let me first compare it to NWChem, which is a library for electronic structure methods, which for the couple cluster methods leverages a prediction global address space library, the global arrays, in order to distribute the matrices and the tensors, and then just essentially reads blocks and does dynamic load balancing. So with respect to that, you can compare the blue lines, this is strong scaling, so down is good, to the orange lines for different system sizes. The orange lines are NWChem, and we achieve much, much better strong scaling. And as we go to bigger problems, so kind of going across the lines, we also achieve better performance, and we are also more memory scalable. This is for CCHD method, so order 4 tensors. This is for CCHD-T, so involving also order 6 tensors. Going further, and now both of the types of lines are our own code, but for CCHD and CCHD-T, and now we just try to do weak scaling, solving the biggest problems that fit into memory and using as many nodes as possible. And kind of what we're able to show is that in terms of the flop rate that we achieve, we're near a petaflop in performance, and we're at a state of reasonable efficiency in terms of the node performance. This is on BlueGeneQ, on Mira, and on Edison, which is a Cray XC30 system at NERSC. We also actually achieve good weak scalability, and we achieve actually an even better percentage of peak. So we are over 50% of peak on 1,000 nodes on that machine. And we actually increase in efficiency because as you weak scale these problems, there's actually more work per byte. So you have kind of a smaller data set doing more computation if you look at the global scaling. Okay, maybe I'll skip the slide. This is just where the time goes, and the point is that we spend most of the time in matrix multiplication. I wanted to talk a little bit about the new capabilities in CTF, which involve being able to have tensors of arbitrary types. So essentially, if any type that is statically sized in Chum++ forms migratable, but we're not quite general to being able to define objects yet. But what we do is we leverage what's the notion of algebraic structures. So you can define an arbitrary type and arbitrary multiplication and addition operators, or just whatever operator you want to define. You can also then define functions, including functions that take two different types and map to a third. So to give a quick example, we can define a semi-ring for path computations and graphs via the following syntax, and then we could define a matrix that's sparse and symmetric hollow, meaning it's symmetric and has no diagonal, to define an undirected graph. And using this, we can implement, for instance, Bellman-Ford as just an iterative scheme involving matrix vector multiplication over the right semi-ring in kind of a trivial amount of code. We can also do kind of more general things where you can define your own type and your own special monoid, and via this implement kind of more general graph algorithms such as between centrality, which can in the end also be formulated as a matrix-matrix multiplication like kernel here done with a function that essentially takes an int in a path and outputs another path, so it's a multi-type function. So this is, I think, closely related to the graph BLAS effort, except we also have support for tensors, but it's very much in a similar spirit. And just to show some quick results of what we're able to do with respect to sparse computations, everything I showed you before was for dense tensors. For doing sparse matrix times dense matrix, we're able to exploit sparsity to lower the cost. So the solid green line, this is weak scaling, this is strong scaling, is the dense version. This is 16% sparse, and each one of the subsequent lines has a factor of 2 less sparsity, and they're just randomly distributed. But the way the cyclic layout works, the particular sparsity structure doesn't really matter. Also means we don't leverage nice sparsity structures. We get better and better performance, and especially as you weak scale, we actually get kind of better and better relative performance. Our sequential performance is bad because the MKL kernel that we use for sparse times dense is at 10% efficiency or less, which one it really shouldn't be, and I think there should be faster kernels. But by the fact that we save the amount of communication by only communicating the sparse subset of the entries, we are able to get better scaling. And finally, to show that we can at least leverage graphs for doing all prior shortest paths by path doubling, where you again can leverage a sparse times dense kernel, we are able to achieve better performance when using sparsity. Although for strong scaling, it eventually runs out and the sparsity doesn't matter so much because you're bounded by latency. Okay, so in summary, CTF is a distributed memory framework that leverages AMPI, OpenMP, and CUDA. And so literally the only dependencies that CTF has are MPI, OpenMP, and the BLAS. There's support for symmetric and sparse tensors or multidimensional arrays, if you will. And I wanted to talk a little bit about similarities to Chum++, which include our use of over-decomposition and virtualization, our use of topology where I'm mapping of these tasks and blocks to different processors, and also the application-driven style of development, which I think has made CTF be something that's quite usable and well-documented. But there are also, of course, critical differences, and I wanted to kind of highlight differences in similar-like things. So we, in a way, do runtime optimizations and runtime kind of choices of decompositions, but we are selecting a regular schedule and a regular decomposition among a subset of those, rather than trying to do dynamic load balancing between irregular decompositions. So essentially, we're migrating tasks between these regular distributions rather than using heuristics to improve them gradually. And also, a key difference between how we do visualization and over decomposition is that we do redistributions on a processor-to-processor basis, and general communication is managed processor-to-processor rather than task-to-task, which in general means that we have a lower synchronization cost and can go between different layouts more easily, but also means that I think in some cases we aren't as dynamic and don't have as much. I think you can also get better cache performance if you just work on a task-to-task basis. Okay, so as future work for the graph computations that I showed, we were using kind of sequential naive kernels, and we need a way to generate essentially dgem for arbitrary element-wise functions. We also only have sparse stems dense now and not sparse stems sparse. And finally, there's a lot of features one can build on top of contractions and also optimize contractions further, including considerations of optimizations that involve not just doing one contraction faster, but a set of them or a sequence of iterative contractions. Also doing convolutions of tensor dimensions, which one would want for deep learning, and doing tensor factorizations, which have many applications, among others. That's all. Thank you. They have turbo boost on?
Yeah, because you get huge amounts of performance benefit from it.
Even, I mean,
For HPC applications?
Yes. It turns out even the least sensitive application, when something like 5 or 8% faster with turbo boost on than off, and that's before you do load balancing to take advantage of faster processors. So the question
Might counterbalance the load balancing because it probably makes the slowest processor fastest, but then, okay.
Well, yeah. So the question I want to ask is, given that you're talking in terms of, static distributions or, distributions that are supposed to be very regular, how does that shift when you're then dealing with processors of, unequal performance?
For now, we pay for that. But, yeah, I guess so far I think they're not that unequal. Even for, currently we're decomposing even sparse tensors, which in a way that essentially is load balanced only up to randomization. So it's not that well load balanced, and you can imagine refining that. But I think you gain so much from the regularity and the ability to exploit very nice communication patterns that it's going to be difficult to try to kind of leverage more dynamic load balancing in the triple plus style and amortize what you're sacrificing with respect to the regularity.
So my question is, it seems to me the issue of regular mapping and distributions versus irregular is a matter of strategy, is a matter of control strategy. The basic over-decomposition scheme can still be utilized, and you can, in other words, you can imagine doing this within Chum++
yes.
with some restricted, right? You can only run on powers of 2 or maybe not squared.
We have similar restrictions, yes.
Right. So that restriction aside, we should be able to. So it should be a continuum that's experimentable within Chum++. Is that true? I mean.
Yes. I think you could implement much of this in Chum++. You would be doing your distribution and communication patterns somewhat differently, which I tried to talk about a little bit, with respect that there you really have the view taken from each char, each block, and those interact directly, while here we're able to infer the fact that the distribution is always regular, and using that make the communication patterns happen on a processor-to-processor basis.
That's inside the implementation.
Yes. So you could use both approaches, but there's some trade-offs. Yeah.
I mean, is it better to express the communication from the point of view of each block or from the point of view of processor? I suppose the expression is still okay from the point of view of block, better probably.
So you have more messages, but you have a better cache locality, I think.
That's implementation, right? You express the communication that way, and then internally you can say, okay, let's aggregate them. We know the regularity, and so let's communicate it accordingly.
Well, aggregating the messages would be difficult, I think, generally, but maybe yes.
I see. Okay.
Are you performing any aggregation inside chars manually of messages?
What do you mean? Here we explicitly define the communication pattern with respect to many blocks. So for instance, we're doing our distributions between 2 different layouts. We'll iterate over all the data that needs to be sent to the new layout. And this is actually also one type of communication pattern that's I think, more difficult to potentially express in Chern++, where you have one multidimensional char array going to another one that's completely different on a different processor grid arrangement. I'm not sure, and essentially you have each block is scattered among some subset of blocks in a newer distribution. And we're able to do that by considering the processor-to-processor level of that, so aggregating the messages of these blocks that each processor owns and communicating all of that to each other processor in a minimal amount of processor-to-processor messages. So you can imagine trying to aggregate this dynamically, but it would require extra work while we do it explicitly. Right. Does that answer the question?
On the dynamic point, I mean, usually when you do these giant tensor contraction things, the size of the matrices and other things are fixed at the beginning of the calculation. So you could probably, unless your mathematics for optimizing your workload is approximate, or the machine isn't what you think it is, you should probably be able to just do it at startup.
Yeah, you can infer all of the tensor sizes and tensor contractions when you run, essentially at runtime, at kind of the first call.
At startup.
Yeah, right.
So you could optimize everything, though maybe if there's a lot
but there's just a lot of them, right?
So if there's overlap and other things, then maybe you get something.
We don't necessarily exploit that, but we might have, and typically do have hundreds of different contractions. So optimizing all of those immediately has value, but currently we're not spending very much time in that anyway. So doing that dynamically doesn't really cost us much, and we do need to do it at runtime. Maybe at startup and only once, but doing it for each iteration of something like CCSD for each different type of contraction within CCSD is not itself so much of an overhead because there are more types of contractions than there are iterations.
Using cyclic layout to do the assignment of elements to processors. Are you also using cache-aligned allocators to avoid full sharing in those situations?
Well, we use aligned allocations, but I think those issues are decoupled because the cyclic distribution is going between processors, right? And for each processor.
You have adjacent elements being assigned to separate processors.
But they're adjacent.
Clarify what you mean by processors? Each one of you, node or core?
Processes, not threads, right? So essentially, each one has a distinct memory mapping, right? So we are. The tensor is never arranged in the contiguous layout in the global sense. It's never in some global memory, right? It's explicitly distributed from the start.
Oh, I thought we were talking about like the CPU level, like the tensor that you would be working on, in 12 cores or whatever, so that locally it would be laid out contiguously. Whether or not it's laid out globally contiguously as well.
So here we would have 12 processes, each one of which has its own memory, so their own shared memory. So they're not reading, nearby cache lines. We just partition the overall matrix or tensor in a way that each process owns a subset of the global thing that is, but it's a contiguous in memory.
So what you're doing a global cyclic
Yes. So locally for the threads, we don't actually have anything that uses cyclicity. There we'll do other partitioning schemes actually. So once we do have a tensor. So we do use threading, but in which case we have kind of a shared memory and have to worry about fault sharing, but we don't actually do cyclic partitioning among the threads. We do a different type of partitioning there.
Thank everyone one more time. And now we have a break until 3:30.
You're losing anywhere from 5 to 20% of the performance.
Yeah, bigger ones you'll lose less, but it's still, if you tell someone slow your processes down intentionally, like you're never going to make the application slower by that.
Well, that's like sometimes the average speed is essentially lowered.
No, the average speed, we never saw a single processor here once said.
You're definitely spending more energy.
If you run for less time total, there's a lot of fixed power costs that you cut. That are just multiplied by your total execution time. So yes, the processors might be drawing more energy, but we don't have energy data in this. Well, we have power data as an instrumentation thing, but basically we never saw processors running all the way down at the spec frequency, and certainly never below it. They were all well above. They were all above, and mostly like way above. Almost near their upper limits. So, everything will go faster than its rated speed. It's just a matter of how much and whether you take advantage of every one of them. And how quickly they can go. So anyway, we can explore this more later. We'll both be in town for a while.
How much load balancer it also causes.
So, implementation of operator bracket. You're taking a string literal. That concerns me.
Why?
Because are you interpreting that at runtime?
Yeah. But we do checks with respect to whether it makes sense to run.
I wasn't worried about correctness. I was worried about if you do it compile time, you can use effectively expression templates and some TMP to get which loops you need at compile time rather than at runtime.
Right. You could do a lot of what we're doing. Essentially, compile time module is the fact that you don't know the problem sizes and you don't know the number of processes, but you do know some things about the problem. But I'm actually a big fan of doing things at runtime because for these types of computations, we might be using hundreds or thousands of cores and nodes, and we only have those at runtime. I'm a big fan of short compilation time and then do your optimizations at runtime.
I'm completely the opposite. The more the compiler knows, the better code it can generate, right?
Yes.
And so the more you can tell the compiler, the better it can do a job.
Yeah.
Right?
But
but at the end of the day, benchmarking is the only answer.